What is up, APs? Welcome back. Today we are going to be talking about statistics in psychology. So we'll talk about how we use data to better understand what it's telling us about psychological phenomena. So don't worry if this is not your forte, if you're not a math person. I'm in the same boat. I am not a huge math star. That was not my best subject, but this is an essential part of psychological research. And I think you'll find that it is actually pretty fun sometimes when you start putting all of your data together and being able to interpret it and come up with some conclusions about psychology. So we're going to jump in and talk about how we use statistics in psychological research. So first of all, what is statistics? Statistics is the branch of mathematics that really is called by some the fun branch of math, because it gives meaning to numbers. For me, I experienced this personally because in high school, I just couldn't care less about Bobby and my word problem and his apples and how many apples he had or how many he needed. But when I went to college and I started doing my own research and I had my own numbers about things that I was interested in, suddenly it was much more meaningful to me. And so I actually really enjoyed learning statistics in college because it had a special meaning to me then. So first, let's talk about some terminology here. When we hear the word parameters, that's a little bit different from statistics. So parameters are numbers that describe a total population. And then statistics is a whole lot. It is the collection, the organization, the description, the analysis, the evaluation, and the conclusions that we get from large sets of numbers, huge sets of numbers that we call data. And when we're looking at statistics, we're looking at large amounts of data and drawing conclusions from those numbers. So there are two main types of statistics that you need to know. The first that we'll go into a lot of detail on today is called descriptive statistics. And it's just like it sounds. It describes data. So this is what we use when we want to summarize our data or organize it in a way or characterize it. So things that we will learn about that fall under descriptive statistics include measures of central tendency, correlation, which you already learned a little bit about, and measures of variability. So first, let's start with the basics of descriptive statistics. To begin with describing our data, we have to come up with what we call a frequency distribution. This is just putting all of our data into an order that makes sense and makes it meaningful. So you are familiar with this. You've learned about bar graphs and histograms in your math classes. That's all that we're really talking about here. So let's say that maybe hypothetically we're looking at test scores. So we have a quiz and the quiz is 40 points total. And so let's say this is all the scores that we got from our class on this quiz. So if we just list it all out, that's great, but we want to put it in a way that is a little bit easier to look at and understand. So we might make a bar graph or a histogram to show this data. This is a lot easier to see what's really going on here, right? We see that the majority of the students got B's and C's, a few got A's, a few got D's, and a few got F's. So this shows us a little bit more quickly what we want to know about our data. So let's practice this. This is pretty easy. I want you to look in your notes, your guided notes, or if you're writing your own notes, then what you're going to do is create a frequency distribution, and then you'll create a bar chart to represent that. So in order to do this, here are let's pretend this is our set of data. So here are all of our scores. We have 13 scores here, all right? And you're going to first just put them in a chart. So on the left side of your chart, you'll put 1, 2, 3, 4, 5, right? So that's the score, 1 to 5. And then on the right-hand column of that chart, you'll tell me how many times that score occurred. For score 1, you're going to put a 2 because there are 2 1s. For score 2, you're going to put a 4 because there are 4 2s, and so on. So I'm going to go ahead and let you pause and work on that, and then we'll come back and I'll show you what it should look like. And we're back. So let's see what this should look like in your notes. So on the left here, we have our frequency distribution. So we've written out how many 1s were there, how many 2s, how many 3s, 4s, and 5s. And then on the right-hand side, we've just represented this data visually using a histogram or bar graph. So we have our scores here on the x-axis, our frequency is on the y-axis. And so you can see there were 2 1s, more 2s, more 3s, and then a few 4s, and the fewest of 5s. So again, this shows us that most of the scores in this set of data were 2s and 3s. So now let's talk about some more specifics of how we can look at our data and understand it better. So one thing we want to ask ourselves when we look at a distribution of data, like we were just looking at, is where is the center of the distribution? What is the central value of that distribution? So we're going to look at measures of central tendency. And these you're familiar with. You've learned about these in math classes before. So there are 3 measures of central tendency we'll learn about, which are the mean, median, and the mode. So the mode is going to be the most common score, the one that occurs the most in a set of data. The mean is the average of the scores. And then the median is the middle score when you place all the scores in order from lowest to highest. So let's say we're looking at the quiz scores over here on the right. If these are all of, let's say we have 5 students, one gets a 4, 3, 5, and then 2 more 4s. So which of these occurs the most? The score of 4. If you add all of the scores together, they add up to 20, and then you divide by the number of scores, which is 5, so our average is also a 4. And then if you put them in order from lowest to highest, it'll be 3, 4, 4, 4, 5. Then the middle value would be a 4. So interesting enough, our mean, median, and mode for this small set of data are the same. And that is very special because when that occurs, then we have something called a normal distribution. We also call this a normal curve because it forms a normal curve, a curve that is symmetrical, and it looks like a bell. So you will hear it called a normal distribution, a normal curve, or a bell curve. We're going to talk in more detail. I'll show you what a bell curve looks like and why it's so important and why we love bell curves. But one thing you need to know is that in a normal distribution, the mean, median, and mode will always be the same value. Now, one thing that's interesting is normal distributions, they are always symmetrical, but they don't always look exactly the same. So you'll notice this one, the blue is a little bit wider and shorter, and the red is closer together and higher. So the distribution, a normal distribution is just always going to be symmetrical, but it doesn't always look exactly the same depending on the data that you're looking at. Now let's talk about what happens when the mean, median, and mode are not equal. So if we do not have what we call a symmetrical normal distribution. This is what we would call having a skewed distribution. So when something is skewed, it's off kilter a little bit. So we have 2 types of skew, and for each of those, it's going to affect your mean, median, and mode differently. So if you look over here on the left, the positive skew means that most of the scores were in the lower range. So let's say this was our quiz. Okay, so this would mean that the quiz was probably too hard because most people did not do well on the quiz, and the higher scores are occurred the least. So in a positive skew, then we would see the mean, but then we see the median is below the mean and the mode is below that. Because remember, if we're skewed this direction, then most of our scores are below the mean. If we look at our negative skew, it goes the other direction, right? So we see that the majority of the scores on this quiz were very high. So this was probably too easy of a quiz. So over here, the mean is right here in the middle of our number line, but the median is higher than the mean and the mode is higher than the median. So these are things that are pretty consistent when you see your data leaning one way or the other, or if it's going to be a normal distribution. Okay, so let's talk a little bit about which of these measures of central tendency is the most useful. So let's say we have found a collection of old baseball cards in the attic, and we want to know how much they're worth. So we go and get them all priced. We have all these baseball players, and here are the prices for their baseball cards. What you will notice is that we have one in particular that is very valuable. Nolan Ryan's card is $1,500. Most of the others are not that high, not even close, right? So let's say you calculated your mean, median, and mode for this set of data. What you would find is that if you include Nolan Ryan in your calculations, then the median, the middle number, is $2.50. But your mean, your average, is $74. So let's say, you walk up with this box of baseball cards and you tell your mom, oh my gosh, Mom, the average baseball card in here is $74. Well, what is she going to think? She's going to think, great, we just paid for your college, right? Because she's going to think that most of them are around $74. But what happened here? What happened is when you calculate the mean, because we have this high number for Nolan Ryan's card, it is skewing the mean. So it's pulling it upward higher than is really a true measure of the central tendency of this set of data. So in this case, because we have this high number, which is what we would call an outlier because it's far from the rest of the data, then it makes the median more useful here than the mean. Now, if we did this without including Nolan Ryan, then our median would be $2.38. Still pretty close, right? And the mean would be a little bit more accurate. The mean would then be $2.85, which is a lot closer to what most of these guys have here. So if you take out the outlier and you don't have an extreme score, then the mean is more meaningful. So that's something that's important to keep in mind when you want to use which statistic to look at the center of your data and better understand the center of your distribution. So again, just to visualize this, here's another example from your textbook. So this shows the income per family in thousands of dollars. And if you look at the data here in each little guy, these are kind of funny looking, they just look like they're sitting on top of each other, but each little guy represents one family at that level of income. So you'll see that the mode here is about $20,000. The median is about $30,000, but because we have this family way over here that makes $710,000 a year, which is insane, they're pulling the average up to $70,000. Well, the reality is that the average family doesn't make that much money. Most of them are on the lower end here. So for this set of data, the median would actually be a better measure of the center of this data. Since most of the data is located here, the median shows a more accurate picture of what most families are making. Now let's talk about another part of descriptive statistics, which is measures of variation. So measures of central tendency tell us where the center of the distribution tends to be, whereas measures of variation tell us how spread out our data is. So there are two ways that we measure variation. The most basic way is by looking at range. In range, you've probably heard of before. Range is just calculating the spread between the lowest value and the highest value, the lowest score and the highest score. So you literally take the highest number and then you subtract the lowest number, and that tells you the range. Well, that's good, but it's not that sophisticated. It doesn't tell us that much. It just considers two of the numbers out of tons and tons of numbers. So a better way to look at variation is through a more sophisticated statistical calculation called standard deviation. So standard deviation is very useful, especially when we talk about normal distributions, and it plays a very important role in understanding your data when you have a normal distribution. So standard deviation, basically it tells us how far on average each score is from the mean. So if we're in a normal distribution, that will be the center, right? So the higher the standard deviation, the more spread out the distribution is. So you can see here in this picture we keep looking at, which of the normal distribution curves has a higher standard deviation. Is it the red or the blue? In this case, the curve that has a higher standard deviation would be the blue because it's more spread out. So which is better? Do you want to have a higher or a lower standard deviation? Well, in our research, we would rather have a lower standard deviation usually because that means there's more consistency among our scores. So a lower standard deviation is usually more desirable. Now, this is how we calculate standard deviation. This is the formula. Do you need to memorize this? No. Do you need to know how to do it? No, you don't need to know how to do it. The reason that I have this here is I will share the link to this video that shows you how to do this. One, if you're curious, and two, just so you can maybe watch it through one time and see how it's calculated so that you can better understand how to interpret a standard deviation. But for now, we're not going to learn how to calculate it. We're just going to learn how to interpret it and what it means. Let's do an example. Let's say that we're a football coach and we are looking for a new punter for our team. So we have tryouts and we have 2 punters, and the first punter comes out and makes 4 punts from these 4 different distances. So 36 yards, 38 yards, 41, and 45. So the mean then would be adding up all 4 of these scores together and dividing by 4, we would get an average of 40 yards. Okay, so the punter number 1 has an average of 40 yards success rate. So then if we want to calculate our standard deviation, first we have to look at how far each score deviated from the mean of 40 yards. So for the first punt, 36 yards was -4 from the mean, right? It's 4 yards below the mean of 40. 38 is -2, 41 would be +1, and 45 would be +5. With me so far? All right, now we are going to square each of those values. So we'll square each deviation, and then we'll add them all together, which gives us 46. Then we'll divide by the number of scores again. So this gives us, with 46 divided by 4 punts, we get 11.5, which is our variance. Okay, so then we take our variance and we use that to calculate standard deviation. So standard deviation, we're going to take the square root of the variance, which gives us a standard deviation of 3.4 yards. So what does this mean? If we have a punter that has makes an average of 40-yard punts with a standard deviation of 3.4 yards. Well, now let's say punter number 2 comes up to try out, and he also gets an average of 40 yards. But let's say his standard deviation is 4 yards. Okay, so which of these 2 punters would we rather have? The one with the lower standard deviation or the one with the higher standard deviation? Well, if we go back, remember that we said a lower standard deviation suggests more consistency. So if we're looking at our 2 punters and we're trying to decide which one should make the team, the one with the lower standard deviation should make the team because he is more consistent. He deviates from that mean, from that average, less often than the other punter. The other punter is less reliable, in other words. So in this case, the punter with the lower standard deviation of 3.4 yards would make the team. Now we're going to take some time to look at the normal curve. What is it? Why is it important? And what are some things that we can assume about a normal curve that will help us to interpret data quickly and easily? So I'm going to go ahead and show you a little bit about that in my classroom. Hi guys, today we're going to be talking about something called the normal distribution or bell curve. This is something that we see often in nature in statistics. So we're going to learn about the bell curve, what are the characteristics of a bell curve, why is it important, and we're going to draw one together. So I want you to draw some with me today. Grab some paper, grab color pencils if you want, or you can just use one color. And I'm going to show you what it looks like and how to interpret things based on a normal bell curve. So first of all, why is a bell curve important? A normal distribution is something that we study because it happens so often in nature. So things like blood pressure, height, weight, all naturally follow this similar pattern that we're going to see here. So basically, a normal distribution is a hypothetical curve that describes the data of a population. So it is something we study because we have noticed in nature a tendency for data to cluster around a central value in a set of data. And when we plot it, it tends to look like this. It looks like a symmetrical curve that, yes, looks like a bell, right? So this is what the curve tends to look like, and you can apply this to so many things. This has been applied to IQ scores. So this central value that I mentioned that this data tends to cluster around is our population mean. And whenever we talk about population mean in statistics, we're going to use a special symbol, and that symbol is a Greek letter mu that looks like this. Okay, so mu is our population mean. So in any set of data, the population mean is going to be the center of that curve. And if you move the mean down, guess what? The curve's going to shift left. If you move the mean up, then the curve is going to shift right. So it's going to follow that mean because everything is clustering around that central value there. So we know that in a normal distribution, some points are going to fall above the mean, some points are going to fall below the mean, but most points are going to be around that central value. So that's why the height of our curve is the highest up here. So let's say this is scores on the AP Psych exam, and this is the number of students who scored that, had that particular score. So we had not very many ones, a little bit more twos, mostly threes, some fours, and a few fives. So that's one way you could look at this and think of this. So another important thing for us to talk about, another important value when it comes to normal distribution curves is the standard deviation. And we're going to represent standard deviation with this symbol, sigma. Okay, this is the Greek letter sigma. This is our standard deviation of the population. So standard deviation, what does that tell us? It tells us how spread out our data is. So if we have a large standard deviation, then our curve is going to be, our data is going to be more widespread. So our curve is going to be a little flatter. So it might look more like this. It's more spread out. If we have a small standard deviation, then that means that it's less spread out, which means that our curve is going to be taller because it's less spread out. So the standard deviation tells us how spread out the data is. The mu, population mean, tells us what the central location is. So now we're going to talk about some characteristics of the normal distribution that you'll be able to apply to different sets of data. So we're going to learn some patterns that happen and then how to interpret what we're seeing up here on our curve. So let's say that we're looking at IQ scores. So our mu, our population mean in this case, is going to be a score of 100. Okay, so that's going to be our central point. This represents a score of 100. We're doing IQ. One thing that you need to remember about normal distribution curves is that if you have a normal distribution, there's one thing that you know will always be for certain, and that is that your mean, your median, and your mode are all going to be the same number. So if our mu is 100, our mean is 100, our median will also be 100, and so will our mode. Which makes sense, right? The median is the central value as well, right? This is your average, and your middle value is your median, and then the one that occurs the most is also that same number. Okay, so those are always going to be the same in a normal distribution. Now, for IQ scores, the standard deviation is 15 points. All right, so that means that if we move up 1 standard deviation here, then we are adding 15 points to our mean of 100. So 1 standard deviation above the mean will equal 115. Then let's go down the other direction. 1 standard deviation below the mean, so negative, I'll put negative standard deviation, would be 100 minus 15. Okay, so that's going to be a score, an IQ score of 85. All right, and we'll continue. If we go 2 standard deviations above the mean, then we're going to add 30, so it'll be an IQ score of 130. Right? If we go 2 standard deviations below the mean, then we're going to subtract 30 from 100, so it'll be an IQ score of 70. If we go 3 standard deviations above the mean here, then we're going to add 15 plus 15 plus 15. That's going to be a score of 145. Very high IQ. If we go down here, 3 standard deviations below the mean, so we've subtracted 15, subtract 15, subtract 15. That's going to be a score, an IQ score of 55. Well, great, that's easy, but what does all this mean? So one thing that we know for sure is that if we're looking at a normal distribution curve, then we know that within this curve, all 100% of our data points are going to fall in this curve somewhere, right? This includes all our data. So every single person whose score we're looking at is going to fall somewhere in here. And the question is, how many will we find where? So we know the most people are going to be around here in the middle, around an IQ of 100. That's the average. But then what about how many people fall between 85 to 100 or between 70 to 100? That's something that we can actually predict because we've studied the normal curve and we've calculated these things. So there are patterns we can identify. So now we're going to add to our drawing here. So let's go ahead and draw a dotted line right at the center here. And mine's not perfect because, you know, I'm human, I'm not perfect. So pretend like that's perfectly centered. All right, so that's our mean, our mu of 100. Okay, now we're going to draw a margin between our positive 1 standard deviation above the mean and our negative 1 standard deviation below the mean. Okay, so within 1 standard deviation, either above or below the mean, all right, we can say, based on our calculations, based on years and years and years of research and the work of scientists and mathematicians, we can say with confidence that there's a certain percentage of our population that will fall between these 2 points. So that will be within, in other words, within 1 standard deviation from the mean. So the number that you're gonna want to memorize these. Okay, so first one is that 68% of the population will fall within 1 standard deviation of the mean. So that means 68% of the population that we're looking at is going to have a score, an IQ score, between 85 and 115. So we're going to draw a line from our standard deviation, two standard deviations above and 2 standard deviations below. This is bigger, right? There's more space. So that means we're going to have a bigger percentage of people that fall within this standard deviation. So for this one, our percentage is going to be 96%. All right, so 96%, that's almost 100 already, right? That's a lot. So 96% of our population falls within 2 standard deviations of the mean. So they're either going to have a score of 2 standard deviations above or below. So in other words, if we're talking IQ, in this example, that means 96% of our population will have an IQ score of 70 to 130. that includes this original set, right? They're still within that. Okay, so of course those people are included now because if you're within 1, you're definitely within 2. So that tells us that our last one here is going to be the largest percentage, right? So 3 standard deviations above and below the mean. So then, all the way over here. So that means that 99.7% of the population falls within 3 standard deviations of the mean. So that's darn near 100%. Almost 100% are going to fall between 3 standard deviations. This tells us that if we're looking at IQ, that 99.7% of the population will have an IQ somewhere between a score of 55 and 145. So that's pretty straightforward, right? You might be thinking, okay, yeah, that makes sense. Okay, that's pretty easy. If they ask me a question like that, I'll be able to get it, all right? Couple of tips for you on the AP Psych exam. Number 1, memorize this. And it might seem intimidating now, but drawing it should help, right? Memorize this as best you can, because if you can memorize this and draw it out at the drop of a hat, if I could say in the middle of class, go draw a normal distribution curve and label it. If you can do that by the AP exam in May, then you're in a good place, because this is a good thing to be able to reference. It makes answering questions about standard deviation or about a population or about normal distribution much, much easier. So now let's look at this example. Marilyn Vos Savant. She claims that she has an IQ of 228. All right, so looking at our scores here, that would be way out here, right? Way off the charts. Okay, and we already know from our normal distribution properties, we know that less than 0.1% of the population has a score higher than 145. So for her to be way out here means she is extremely rare, extremely intelligent. So the question then is, if we were talking about Marilyn Vos Savant and we were talking about her intelligence, would it be more meaningful for us to say, Marilyn has an IQ of 228, which is 128 points above average? Or is it more meaningful for us to say, she has an IQ that is 5, 6, 7 standard deviations above the mean? Well, anyone who knows their statistics would say the standard deviation is much more meaningful, because that shows just how rare that is, instead of just saying she's so many points above the average. Another type of statistics you need to know about is called inferential statistics. Now, when we talk about inferential statistics, this is what we use when we want to compare differences or find statistical significance or draw conclusions. In other words, when we use inferential statistics, we are inferring, which means we were taking what we know, what is known, and then we use it to make predictions about the unknown, but possible. So this helps us to make predictions about things that we don't know yet, but we can make really, really close conclusions and comparisons and predictions based on what we know. So a major part of inferential statistics is probability testing. One of the things we'll talk a lot about when we talk about inferential statistics is called statistical significance. When we talk about significance, we're talking about the probability that the results we have, say in an experiment, are due to chance or a fluke rather than the treatment or the independent variable. So in other words, if I ask about statistical significance, I'm asking, how certain can I be that the results of my experiment were caused by the independent variable and not some random chance? So obviously, as an experimenter, I want that chance of a fluke to be very small, and I want my certainty to be very large. So what does this look like numerically? Well, we calculate statistical significance by calculating something called the p-value. Again, you don't need to know how to calculate this, but you do need to know how to interpret it. So a p-value is just telling us the likelihood that the result was caused by chance, and it can't be greater than 5%. So if it is greater than 5%, then we know that our results are not statistically significant. So remember what I said, we don't want the result to be a fluke, so we want a very small p-value. And scientists and statisticians have sort of come up with this arbitrary number saying that 5% is a good, that's close enough, right? That means we're 95% sure that our independent variable caused the results that we had. So according to this statistical significance, this threshold that has been chosen by scientists, 6% is not good enough. 5% or lower is good, but 6% is too far. So in other words, if p is 0.06 or 6%, that means I'm 94% sure that the results of my experiment were due to the independent variable and not a fluke, and that's not good enough, so I won't publish my results if it's not 95% or higher certainty. Then, if p is less than or equal to 0.05, then the result would be considered statistically significant. And the last thing I'll say about p-values is to remember that because it's a percentage, it can only range from 0 to 1, so 0 to 1.00. So it's either 0% or 100% or somewhere in the middle. And of course, remember that if p is 0.05, that means that there's a 5% chance that this was just a fluke. This was just random and just by chance. And then it also, if you want to say it a different way, means that we are 95% sure that our result was due to what we did as the experimenter, what our independent variable was causing. So that is statistical significance. And that's all I have for you guys for our statistics notes today. So I will let you go and we will talk more about this on Zoom. So I'll see you later. Bye!